if we kind of think back to what we've talked about so far, we had the Big Bang, we built the Earth. It was pretty big ideas. Again, take a geology class. I'm going to say that over and over and over again. Because these are really cool ideas. We don't necessarily have all the time to get into them in this class, because it's a climate change class. I have not forgotten that. But the last thing that we really talked about was the notion that once we have Earth's dynamo built, and we have Earth's magnetic field in place, we now have essentially protection, right, from these ion blasts, or what we call solar winds. And things start just kind of doing their thing on Earth. So we've got the Earth here, and one of the things that's really interesting when we go back to really early Earth, we call Hadean Earth or even Archean age Earth. Those are some of the two earliest kind of geological kind of units of time. The heat inside of Earth, the heat that's responsible for, earthquakes, which is plate tectonics, right? The heat that's moving the plates, volcanic activity, all of that stuff is really generated two different ways. It's generated from pressure, because pressure generates heat. But most importantly, it's generated from elements inside of the Earth that are undergoing radioactive decay. So they go through radioactive decay, and part of that process is they emit energy, right? Heat energy. So I'm not sure how much you know about exponential decay and all of that, and I'm going to skip the details, but what I'm going to tell you, and you just kind of trust me here, is that early in Earth's history, there was a much higher percentage of radioactive material because it actually hadn't decayed yet, right? That takes time. So all of these geological processes that we think about, namely, plate tectonics and the volcanic activity associated, was happening at a much faster rate. There weren't big continents yet. The atmosphere, as it begins to cool up, does some really interesting things. So we start to have what we call outgassing. And that is the material that's kind of ejected from Earth by these volcanic activities, so volcanic outgassing specifically. And so the early Earth's atmosphere, now that it's protected from these solar rays, basically is just stuff spit out by volcanoes. So I'm going to kind of write down a quick little list here. Lots of stuff. And oddly, I drew them inside of the Earth and out in the atmosphere like they'd be. But we've got CO2, H2O, CH4, which is methane, NH3, which is ammonia, SO2, that's sulfur dioxide, sulfur, chlorine, again, and a host of other things, other noble gases and such. Nowhere on here is oxygen, right? So early atmosphere didn't have any oxygen in it. But some interesting things start to happen. So now we can kind of think back to, we're going to zoom in and think about what's going on with the atmosphere. So I just recreated a few of these things. You can see, down here, here's your buddy standing on the Earth. Presently, these compounds aren't in very high concentrations in Earth's atmosphere. But that was not true in the beginning. And one of the things that I want you to notice, because we're going to come back, but they have multiple atoms in these molecules. And again, we don't necessarily have time to back through and go, into how molecules form. That's content for a different class. But one of the things to note is that each, so that's a carbon, that's a hydrogen, that's a nitrogen, a hydrogen, 3 hydrogens, carbon, oxygen, 2 of them, sulfur, oxygen, 2 of them. Each of those atoms will have different weight. And once you have molecules of different elements, one of the things that they can do is they can absorb energy. So we call these, the suite of these, the greenhouse gases. You've definitely heard that term. You're not going to understand it in this video. We're going to really go through a slog and understand how they work. So at this point, just these are greenhouse gases. And one of the consequences was CO2 in particular, in early Earth, was about 200 times the concentration that it is today. CO2 is not the strongest greenhouse gas, but it's really in high volume. There's lots of it. And that's why we're going to talk about carbon for the rest of the semester in this class. But But early in Earth's history, one of the things that I talked about was that the sun, which was really in its infancy, the sun had just been born and hadn't really gotten up to full nuclear fusion yet. Well, it had gotten a nuclear, but full bore, like all of the different chain reactions acting, so still early. So it was about 70 times as bright, so giving us about 30% less energy, although the surface of the Earth was much, 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 much hotter, like similar to Venus hot, like liquid lead on the surface of the Earth hot. And the reason is these elements, or these molecules, elements within these molecules, but these molecular configurations store energy. So it's like having a 30 degree below zero sleeping bag, like really good insulation, right? That's not necessarily the case anymore. But generally, some of the first things that start to happen is the Earth begins to cool a little bit now that there are gases in this kind of steamy, foggy atmosphere. And one of the first things that starts to happen is it begins to condense and fall as precipitation, particularly this guy, H2O, which condenses at fairly low temperatures. And it's easy to condense. The energy isn't kind of the negative sense energy isn't that high. So it basically begins to rain. And that is where we start to get the first surface water built up. So when we look at, in particular, these zircon mineral crystals, take a geology class, that's not super important. But we know that we have interaction with surface waters on Earth at about 4.2 billion years ago. Earth is 4.56 billion years. Basically, immediately, or a couple 100 million years into Earth's development, it started to have liquid water, surface waters. And the other thing that starts to happen is when you have that rainwater falling through the atmosphere, it will actually undergo a chemical reaction with CO2. So I'm going to just write this here. This is an awkward position. So H2O plus CO2 goes to CO3. You can't even read that. It's probably got reflections on it anyways. But H2CO3 is what we call carbonic acid. And so rainwater will combine with CO2, and when that acid hits rocks, this is something we're going to talk about in like week 7. When it hits rocks, it causes a chemical reaction, and it consumes that CO2, and it becomes rock material. It becomes sequestered into the rock cycle. And that's actually what we call the slow carbon cycle. And so actually, CO2 is slowly being stripped out of the atmosphere by rainwater. It doesn't happen very quickly, but it does happen, still happens today. Rock weathering is reliant on that. We start to have CO2 being depleted. Some of these other gases are here, nitrogen and hydrogen. The solar radiation, so now we have basically no ozone, no real atmosphere that's protecting us from ultraviolet radiation. It begins smashing these apart, so there's now free nitrogen. Hydrogen can oftentimes just float up into the atmosphere. And so all of this slowly starts to change. So we start to see more free nitrogen, and nitrogen will actually just bond with itself. So N2, free nitrogen in the atmosphere. Most of our atmosphere is nitrogen, 80% of it today. CO2 starts getting stripped out, but it's still not a very nice place. There is one... We're now going to kind of skip past this. So once the collision of Theia happens, it kind of ruins all of this, but it doesn't ruin the dynamo, or it doesn't break the magnet of Earth. Earth still has a magnetosphere, and all these processes are still operating. Volcanoes are still going on. These steam clouds of gases that are condensing and raining back down, that continues to happen. So everything kind of rebuilds after that. And then when we get to about 3.6, 3.8 billion years, something really interesting starts to happen. We see the appearance of life, particularly in the form of something that we call cyanobacteria. And they start to form these mounds or like slime mats. So basically the stuff is slime, but organic slime, and it's still around. So cyanobacteria is the first thing on Earth that can actually carry out photosynthesis. So the first life doesn't have photosynthesis. So the evolution of cyanobacteria, it develops pigments that can allow it to carry out photosynthesis, particularly chlorophyll, if you remember your high school biology or your college biology for that matter. And what happens is we start to get this revolution. Let me decode this drawing. So this is what we would call a stromatolite, or an algal mound, a colony of these cyanobacteria. So sometimes they're in these kind of mound shapes, other times they're just kind of mats of slime. But generally they have to live in water, right? So early Earth, nothing lives on land for a very, very, very long time. But these things live near the surface, so we call that the photic zone, so they can get light and create photosynthesis. I drew a kind of mound version, and actually I kind of zoomed in on the surface of the stromatolite, so these things tend to be layered. And if you were to look really closely at the surface, you'd see all these little filaments that are cyanobacteria. And they die, and new ones grow, and so these mounds kind of evolve over time, and they're still around. Like I said, there's turns out once other things evolve, these don't do that well because things like to eat rock slime. But at this time there was no competitors, so rock slime ruled them all, right? It was the king of the castle. It was actually the only resident of the castle, so by default the king. So these little algae bits, they are carrying out photosynthesis. That's huge. And so actually at this time, this is when we start to see CO2 getting consumed by photosynthesis. We're going to go into the chemistry of that later in the semester, so we don't need to go through it right now. And emitting oxygen. So prior to this, we really only had what was called the slow carbon cycle. And that was CO2 in the atmosphere getting stripped out by rainwater. Now, and then reacting with rocks and becoming deposited as rocks, erupting from volcanoes, emitting more CO2 into the atmosphere. That happens very, very slowly. The residence time of a CO2 molecule is 500,000 years, 500,000 years. Slow. But here, we start to see part of what we call the fast carbon cycle. And that really is the balance between photosynthesis and respiration. So you've likely, been aware of the fact that plants produce oxygen, humans consume oxygen, and all animals, and we release CO2. But only half of that has happened here. So we have cyanobacteria consuming CO2, producing oxygen. So now the global CO2 levels start dropping, and actually oxygen starts increasing. And that fundamentally changes the atmospheric system of the Earth. Now, one thing to keep in mind is that the fast carbon cycle does not yet have a balance. So here are two words I'm going to introduce that we're going to talk about later in the semester, or throughout the semester: source and sink. So when we're thinking about CO2, at this point, we have sources, pretty much one, and those are volcanic, that's volcanic outgassing, that's our CO2 source. But a sink, that's the opposite of a source. That's something that's consuming it, right? Sinking it down the drain, if you were to think something like that, where it kind of sucks up CO2. So now we have photosynthesis as a carbon sink, and we also have Rainwater is stripping CO2 out of the atmosphere. It's reacting with rocks, ending up as rocks in the rock cycle. So we start to see more CO2 sinks, less CO2 sources. But what we're about to investigate, and I'm actually not going to get into it this week because we do cover it in later weeks, is that this system is out of balance in the early Earth. So we've just talked about how we now have all these ways to get rid of CO2 and very few ways to get it back. So globally, the CO2 levels start dropping, and remember that CO2 is the primary gas in Earth's atmosphere that is responsible for temperature regulation. So as this starts to deplete with nothing replenishing it, things are out of whack and things get pretty goofy. The Earth gets fairly cold. We start to get into something that we call snowball Earth. The carbon cycle in general, and thinking about an atmosphere that's something similar to what we see in the modern world, it really doesn't kind of reach a point of equilibrium until animals evolve, which takes a really long time. But once they do, now we have respiration, which is producing CO2 at a fast rate, and photosynthesis, which is consuming CO2 at a fast rate. So when we talk about the fast carbon cycle, the biggest source of CO2 in a year, in any time in kind of modern world, is animal respiration, but that's balanced by the largest sink, which is photosynthesis. There's lots of other things involved there that we're going to spend the semester investigating. And that'll do it. All right. Well, hopefully this didn't hurt your brain too much. And I'll see you next time, and I'll probably be standing up. I hope. All right. Bye.